third important classification is the concept of linear system and nonlinear system. In a linear system, if an input x1 of t, I am talking about a continuous time system now. This is that our discussion will be mostly in terms of continuous time systems. At a later point in time of time in this course, we will talk about discrete time systems in a specially, but wherever examples are given, we talk in terms of continuous time systems now for the most part. If x1 of t gives rise to an output y1 of t and x2 of t gives rise to an output y2 of t, then for a linear system, no matter what x1 and x2 are, a constant times x1 of t plus another constant times x2 of t will give rise to an output which is c1 y1 of t plus c2 y2 of t for all constants. C1 and C2. This is what is referred to as the principle of superposition. Sometimes people refer to this, break this up into two parts, homogeneity and additivity. What they say is, if x1 of t gives rise to y1 of t, then c1 x1 of t gives rise to c1 y1 of t. That is called the principle of homogeneity. Then the second part is, if x1 of t gives rise to y1 of t and x2 of t gives rise to y2 of t, then x1 plus x2 will give rise to y1 plus y2. That is called additivity. But now we will combine these two together and we will say c1 x1 of t plus c2 x2 of t will give rise to c1 y1 of t plus c2 y2 of t for all constants c1 and c2. And this is the class of systems which are called linear systems, one which obeys this principle of superposition. And most of the electrical networks that we have solved earlier belong to this class. But you must keep in mind that this particular superposition principle will be valid, for example, in the case of electrical circuit with zero initial stored energy. If a capacitor has got some stored energy in that, this principle of superposition will not be valid. Let us take an example. For example, I will say this is applicable to linear networks as a special case, of course, with no independent sources or stored energy. Important. For example, this is a linear network resistance. Suppose I have a source here, 2 volts, 1 ohm. Then if I have an input here Vi, and I will take the current to be my response quantity, I equals Vi minus 2 divided by 1, or Vi minus 2. And if I have two different voltages V1 and V2 and find the currents I1 and I2, and if I say if I have V1 plus V2, then I will not get I1 plus I2. As you can see, for example, I1 here is Vi1 minus 2 for one particular excitation. For a second excitation I2 equals, it is Vi2 minus 2. But suppose I have a single excitation which is equal to Vi1 plus V2, then the current would be Vi1 plus Vi2 minus 2. That will be the current when I have a single excitation Vi1 plus Vi2. But I3 is not equal to I1 plus I2. Why? Because of the source here. I3 is not equal to I1 plus I2. So when you apply this linearity principle or superposition principle, you must make sure that you are applying it to a network which does not have sources or stored energy for that matter. Let us take a second example to illustrate this second point which I have in mind. Suppose I have a capacitor which has got an initial stored Vc, this is C, and I have a current source as excitation. So I will think of this as a system with Is as the input quantity and Vc as the output quantity. Okay, and let me assume that Vc0 equals some rho volts. That is the initial capacitor voltage is so many volts. Then you have the relation Is equals Vc equals 1 over C 0 to t Is dt, that is the additional charge that is conveyed to the capacitor in the interval from 0 to t. This is Vc of t, plus the initial voltage that is across the capacitor rho. That means this initial voltage plus the increment in the voltage due to the additional charge that has been conducted to the capacitor in the interval 0 to t. This is the equation between the input quantity Is and the output Vct. Now let us take a situation where I have Is is, there is one Is1, then you will get Vc1 equals 1 over C integral Is1 dt plus rho 0 to t, of course. And let us take a second excitation which is 0 to t Is2 dt plus rho, that is Vc2. So Is1 and Is2 respectively will give rise to these voltages Vc1 and Vc2. Suppose I had a single source which is Is1 plus Is2, both of them are acting in parallel simultaneously. Is1 and Is2 together charging the capacitor. Then the third time the voltage Vc3 will be 1 over C integral Is1 plus Is2 dt plus rho, again because initially the capacitor is charged to rho volts. Now you can see Vc1 plus Vc2, which are the responses due to Is1 and Is2, will not add up because Vc3 is not equal to Vs1 plus Vc2. What spoils is this initial charge in the capacitor, because when you add these two up you get 2 rho, but it is only 1 rho, which means that the argument is that this principle of superposition is valid only for systems which are purely linear, in the sense that they should not have any sources inside, independent sources, or initial charges on the capacitors or initial currents in the inductors which are always considered to be equivalent to sources. So this is an important principle, and to keep in mind when you talk about linearity of systems. A system which is not linear is of course called nonlinear. The difference between the linear system and a nonlinear system is a linear system is governed by linear differential equations. And a nonlinear system by nonlinear differential equations. What is the meaning of a linear differential equation? Linear differential equation is one in which the coefficients of the various derivative terms, coefficients are not functions of the dependent variable. I will take some examples later on. So if I have a term like d squared by dt squared, its coefficient could be either constant, it could be a function of time, but it can't be a function of another derivative of y or y itself. So linear differential equations are the one which govern the operation of a linear system, and if the equation fails to be linear, then it becomes nonlinear, and that the superposition principle will no longer be valid. We will take up some examples of these equations which govern the performance of the different kinds of systems in the next lecture. But let me stop at this time and briefly summarize what has been discussed so far. Starting with the scope of the course, which is mainly the dynamic performance of linear time invariant systems and networks. We had a look at the reference and textbooks that you may use for following this course. Then I mentioned the background material I assume that you have had before taking up this course. Then we looked at the meaning of a system. Broadly speaking, we said system is a collection of objects or system components united through some form of interdependence among the various constituent components. We said a network is a special kind of system in which all the variables will be of a particular kind, or one kind. An electrical network, a mechanical network, given as examples. And then we also talked about the modeling of a system. Modeling of a system is done in the form of ideal components put together to constitute the system, interconnected in some fashion. And we do this idealization keeping in mind on one hand that the complexity of the system should be not too large to vitiate convenient handling of the model. At the same time, it should be sufficiently realistic so that the results obtained from the model are generally realistic in practice. Otherwise, the model has to be refined once again. I also mentioned that the model and system, we use the two terms interchangeably, almost as if the model itself is a real system, which is of course not true. Then we looked at the representation of a system, and we talked about the multiple input, multiple output system and single input, single output system. And then we went on to discuss the various kinds of classifications of systems, because as I mentioned, we are talking about linear time invariant systems. Therefore, we must know what they mean. So with that in mind, we looked up at we are trying to find out the classification of the important classifications of systems. We talked about the difference between static systems and dynamic systems. We talked about the difference between continuous time systems and discrete time systems. And lastly, we have talked about the difference between linear systems and nonlinear systems. The discussion on the linear and nonlinear systems is not complete, because I would like to give some examples of the governing differential equations for both the types of systems, and we'll pick up at this point in the next lecture and continue our discussion from that point onwards.